So today we are going to discuss another emerging non-volatile memory technology, which is magnetic random access memory, MRAM. So this is the outline. First, we will talk about the building structure for the MRAM, which is this magnetic terminal junction, MTJ. And then we will talk about two kinds of MRAM memory cell. First one is Field-MRAM, or sometimes people call it toggle MRAM. Toggle. So the second one is this STT MRAM. And if the time permits, we may also briefly talk about SOT MRAM, which I don't have slides, but we can briefly talk about that. This one is still under the research. But the first two, this one, the first one is in the product. The second one is almost there. So let's look at the MTJ first. So this is the building block for no matter which MRAM memory cell later we talk about. This is a basic structure. So this is based on this kind of stack. We have two ferromagnetic layers separated by a very thin terminal oxide barrier. And the ferromagnetic layer, as we discussed before, you can think that as little magnets with some polarization state. So it's next to the North Pole, South Pole. But here in this design, we are going to fix, let's say, the pinned layer. The magnet orientation is always to the right by design. And then the free layer on the top, we can change the orientation of the magnet by different mechanisms we will talk about later. That's how we differentiate from the Field-MRAM to STT MRAM to SOT MRAM. So basically the difference is how you change the top free layer. What kind of mechanism you use will determine the type of the MRAM. But no matter what, if you can change the orientation of the free layer, then you can have those two configurations. One is this parallel configuration, where you have the smaller resistance, and then this is the anti-parallel configuration, where you have larger resistance. So here, when you read the resistance, you are going to apply a read voltage to the top layer, and then you measure the current through this structure, and then you will determine the resistance based on the read voltage divided by the readout current. So this is the basic structure of the MTJ. So any questions here? And actually, the MTJ structure is very complex. If you really build this structure on your chip, it's not as simple as just the 3 layer we showed in the previous slide. In reality, you may have like 8 layers or even 10 layers of the ferromagnetic materials as shown in this kind of stack. So what we typically draw is only this part, the pinned layer and the free layer and the terminal barrier. But in order to pin the bottom tier, you may have to design other seed layer or the base electrode to help you to pin the orientation of this one. So it's very complicated. And the material system is typically use this kind of ferromagnetic materials. So typically you will involve like cobalt, iron, those magnetic elements. And the terminal barrier is typically the MgO, like 1 or 2 nanometer MgO, very thin oxide. So this is very complicated. This is through the, let's say, the TEM image. you can see different layers under the microscope, and each layer is typically very thin, a few nanometer. So the fabrication is not easy for this MTJ structure. And in terms of the mechanism, why we have different kinds of readout currents if we have two configurations, the parallel and anti-parallel, is because of this spin-dependent quantum tunneling. So I don't want to get too deep into physics, but as you may know, the electrons have the spin state. So this is inherent to the electron. Each electron will have two spin states, spin up, spin down. So this is due to the quantum mechanics. And the reason you have this kind of different resistance states is because the energy shape of those two states will be spin dependent. For example, if let's say in this case, pointing down, we'll have this kind of energy diagram. This is the energy, this is the density of states. So basically it says how many states available for those electrons. And because of the ferromagnetic material, you have this difference in the spin up and spin down. This is spin up and spin down. So if you have the parallel kind of configuration, so those two energy diagram will be the same, right? So they're parallel, so that means they're the same. So here the spin down electron will dominate in those two layers. And if you apply voltage difference between those two electrodes, or let's say you apply voltage to the right, then you are going to bend down the energy for the right. So by this amount. So then the spin down electron will tunnel through this structure. And you have a relatively larger current here because you have enough states here to receive the electrons from here. And spin up is very few because first of all their occupation is less. So this is a low resistance state, higher current. But let's look at the other configuration where you have anti-parallel states. So that means you are going to flip the energy diagram like this. So in this case, this one spin up state, you will have more spin up electrons in the right hand side here. So in this case, you will see that the spin, if you still apply the voltage here and bend down the energy, so the spin down electron here will tunnel through. But here the density of states is less. That means you have less empty states to receive the spin down electron. That's why the current is smaller compared to the parallel states. And then for the spin up electrons here, you will have less spin up electrons to start with. So you will have less current as well. So overall, you have less current in the anti-parallel state, and that's the high resistance state. So this is totally due to this quantum tunneling based on the spin polarities. So this is due to the physics. I will not talk too deep into here. And for the device resistance, we will define this TMR ratio. This is the internal limb magnetoresistance ratio, and it's defined as the back. So it's defined as the difference between those two resistance divided by the parallel state resistance. Let's say the anti-parallel resistance minus the parallel resistance divided by the parallel resistance. And if the on-off ratio, that means RAP divided by RP is 2. If you do that, then it's like 2 minus 1 divided by 1. So that gives you 100%. So if you look at the literature, it says like 100% TMR ratio. That means on-off ratio actually is 2. And you can tune this resistance change by using the magnetic field directly. So if you have this kind of structure, you can apply the external magnetic field to tune the free layers orientation. Of course, if you apply magnetic field, M field, externally to the left, then the free layer will point to the left. If you apply the magnetic field to the right, then the free layer will point to the right. And then you can measure the resistance difference between those two states, and you will get this TMR ratio. Of course, this is by the external magnetic field. This is only used for testing purpose. In the integrated circuits on chip, you don't apply external magnetic field. You use electrical mechanisms to change the state. So the TMR ratio, as you can see, is very small actually, right? So on-off ratio only 2, TMR ratio like 100%. It's really small compared to other memory technologies we talked about so far, like RRAM phase change memory or even flash. The on-off ratio of those technologies can be like 10, 100, even 1000. So this one is very small on-off ratio, like 2. So first of all, it will impose challenges to your peripheral circuits design, especially the sense amplifier. You need to sense such small difference. So it's quite challenging. Second one is because on-off ratio is only 2, so essentially this is like a binary memory. Very hard to achieve multi-level cell. Because in principle, if you want to achieve multi-level cell, you will insert the resistance levels between the very on and the very off states. But in this case, the very on and the very off actually only differs by two times. So it's very hard to insert additional steps between those on and off. But in the recent years, there are some progress to change the material and to improve the TMR ratio. And the record is actually 600% TMR ratio. But I would say this is only in the paper. In reality, if you look at the typical data from the foundry, still the TMR ratio is like 100%, at most 200%. That means on-off ratio like 2 to 3 at most in the large scale integrated array. Okay, so let's talk about what's the difference between this field toggle MRAM and this STT MRAM. So the difference is that the way you write the cell. So that is how you change the orientation. So in the field MRAM, this is a typical structure. You do have a transistor as a selection device, and then you have this bit line, and then there is a right word line and read word line separate. Okay. So this right word line is placed directly underneath the MTJ structure. Of course, here is not, there is a gap here by isolation. So the way you change the orientation is to pass a large current through this rightward line. So you pass current and then you will generate the magnetic field. Why is that? Any idea? If you pass current to that rightward line, then you will generate magnetic field. Why is that? If you recall your high school physics. So if you have changing current, right, so the EM theory tell you, right, let's say use the right hand rule, right? So then you will generate if you have current flow this way, then you will generate magnetic field surrounding this line, right, using the right hand rule. So then essentially you are generating the magnetic field here. Then in this case, you are going to tune the free layer to point to the right. If you want to point to the left, what do? You reverse the current direction here, then it will generate the let's say counterclockwise field. So this is how you change the free layer orientation. And there are challenges with this kind of structure we'll talk about later. So the second mechanism to change the orientation is by this so-called STT. It's short for spin transfer torque. And this is by directly applying current to this structure. So in this case, it's like 1T1R cell. You have one transistor, one resistor. To change the orientation, you just pass the right current directly through this structure. We will talk about how this happens in the later slides. But here you don't rely on the fringing magnetic field. So in this case, the current directly goes through the structure to change it. Of course, you need larger current to change this. So, any questions here? All right.
What's the transistor for the Field-MRAM?
You still, when you read this cell, you need to select this cell. It's like 1T1R. You need to select which cell by the decoder. So then you need to use transistor to locate the cell in the memory array.
Sorry. If we do the right operation on the first structure, the right operation will write all the cells on the same.
Oh, that's a good question. So this is a half-time select issue. We will talk about it in a minute. So it's like a crossbar array. You should avoid that. So we'll talk about that in a minute. Okay, so let's look at the Field-MRAM first. So this is a cross-sectional view for the memory array. And you do have the transistor for the read operation. This is down to the substrate. And then in the contact layer, you build some interconnection between the different layers. And then you are going to build the MTJ structure between some top metal layers. Let's say in this case, metal 2 and metal 3. But as we discussed, you need to insert this rightward line underneath the MTJ because you are going to rely on this to generate the magnetic field. So here are some real images from, I think, IBM's chip. So the MTJ is here between metal 2 and metal 3. And this guy is the rightward line underneath the MTJ structure. So this is MTJ, and this is the right word line. So this is to answer your question. Yes, you may have this problem, right? So if you apply this current to this right word line, so along in the memory array, you have the rows and columns. So along this right word line, all the cells will see this magnetic field. So essentially, this is very like a crossbar array, and you need to design the structure that only when you have this top bit line also carrying the current, then the intersection between the red word line and the bit line, this cell will have enough magnetic field to flip the orientation. So the other cells, for example this guy and this guy, will only see the magnetic field from this current. And we hope that this is not large enough to change the orientation. So it's like the crossbar array, you have the V and 0, and then those are like half-V biased. So this is just an energy with that. Of course, this is not like a V and half-V stuff. But this is the same situation as that crossbar array. You need to design this to make sure only the selected cell at the intersection will have enough magnetic field to change the orientation. The other cells along the right word line or along the bit line will only see half of the field, and you hope that half of the field will not change the state.
This is for F squared, right?
No, this is we just show this top layer. Underneath you have transistor. Remember? We just show this part. You cannot have tight pitch like that. You still need to embed the transistor underneath. So here we only show the top part. So this is one of the problems with the Field-MRAM, which is this half select issue. And actually, the Field-MRAM has some products with like 16 megabits capacity, and here is done at 180 nanometer, and this is a chip area, and you can read all the details here. This is by the IBM, I think. So the great challenge for this Field-MRAM is the right current. If you look at the specs here, the current to write the cell, that means to change the orientation of the free layer. If you want to do this within 30 nanoseconds, you need to pass 80 million to the right word line. 80 million is a huge number. If you are familiar with any circuit design, right? 80 million, even 1 million is a huge number to work with. So this is very large, very power consuming. This is a key problem for the Field-MRAM, because it relies on this fringing field, fringing magnetic field, right? You pass current, and you hope this current will generate the surrounding magnetic field. So this current needs to be very large to generate strong enough field. So that's why this technology does not scale, because this current is too large. And later,